Hi Veronica, this is just a recap video of everything we did on Monday night. I've actually done this video already, but my computer crashed, so I'm going to have to do it again. So hopefully I will remember everything I said last time, and you can understand what I'm saying. So first of all, these are the things we covered: fundamental theorem of calculus, integration, and so on. So I'm just going to talk about each one a little bit, just as a recap for you, because we went through it and you've got the notes. So if you want to refer to the notes as we go along, that's going to be a big help. Second, if I ask you a question in the video, just pause the video and think about the answer, just for a moment. Think of what the answer is, and then I'll say what the answer is when you press play again. So I might say pause, I might just ask a question as if you're there. Just pause it, and it gives you the chance to think rather than sort of passively just listening. Okay, so fundamental theorem of calculus. What is it? Can you remember what it looks like? What's in it? Why it's like that? Can you remember the actual equation? So it's f dash of x equals what? So now's a good time to pause, maybe write down what you think it is, or just have a think about it. So I've already written this down, so it's going to be a lot of me clicking as it rewrites everything that I've said. So remember that the key thing with differentiation is it looks at the change. So the change is the function's increased by a little bit. Remember, initially I said that just a number 1, then I said it was dx. These aren't considered rigorous names, so we use h instead. It increases the function a little bit by h. And if we take away the original function, that will tell us the total change. So you think about the square. When I increase that square of sides by 1, or by dx, it increased the area of the square. And if we take away the original square, the area that's left is the change in the area. And that's all that means. That's just a mathematical way of saying this is a change. If we then divide it by h, it's going to give us the change per step, because the step size that I made, 1, dx, h, whichever we call it, if I then divide by it, it's going to normalise it, tell me what it is per step. And that's what gives us the rate of change. For not very good accuracy, but infinite accuracy, what we then do is let h tend to 0, i.e. we want h to be as small as possible. So h will tend to 0, and we get smaller and smaller and smaller. That's called a limit. So that's the equation. F dash of x is equal to limit of h tends to 0 of f of x plus h minus f of x over h. So I know that's all letters and it's horrible, but like I said, all it's saying is that something's changed. What's the rate of it? Then we looked at integration. I'll look at integration and what that is. So, what is integration? Another time to pause the video. What did you think of? Hopefully you recalled that differentiation and integration are the reverse of each other. Yeah, that's true. But we can't just say integration is the reverse of differentiation. We need to explain it without using those words really. They both share the same kind of pivot thing, which is that they both concern changes. So for differentiation, there's a change made when the area increases for the square, for example. And then we want to know what the rate of that is. So what happens every step? How quickly does it change? Integration tells us the sum of all the changes. So if you start off with a small square, and then it increases by a bit, increases by a bit, increases by a bit, and so on, what's the total change? And what's clever about integration is that each change will be different, but it'll add them all up rapidly, whereas multiplication, it can only add up things that are the same, like 3 times 5, you add 5 3 times, it's the same thing. But integration adds up different things just as quickly, and so just like differentiation is very accurate. An analogy for that would be differentiation is your speedometer. It tells you the rate of change of distance, so how quickly that your car passes, moves in an hour. That's a normalised measure. So you do 50 miles in an hour, your speedo will say 50 miles an hour. It's just telling you how far you're going to go in that time. It's automatically normalised. If you were to vary your speed a lot and do lots of different trips, which is what the reality is, you'd have an average speed. The mile counter doesn't care about the rate of change, it just adds up all the changes. So even though all those different journeys would have been different speeds, different distances, doesn't matter, adds them all up and gives you the correct answer as well. Not very accurately, but integration is far more accurate than that. You could move your wheel a nanometer, and integration would tell you that. Less than that, you could barely move it, and integration would be able to measure that. So we looked at a few integrals. Integral of y equals 2, so that's a horizontal line that's down there. What was that? And using the rule, increase the power by 1 divided by the new power. That's going to be 2x plus c. Why? Well, because the y equals 2 is going to give us a rectangular shape. The height of it is 2, the width of it is x, so the area of it is 2x. So when we integrate, because of all these changes, it adds up all the changes that are made and gives you the area underneath the curve. So for y equals 2, it's going to give us a rectangle. Then we looked at x, and y equals x gave us x squared over 2 plus c. And that's the area of a triangle. So those two things coincide with our normal way of calculating areas, which is kind of a confidence builder, really, that we're doing something that seems completely different to just finding the areas of a shape. But we still get the same answers, so that's good. So when it comes to doing things that are curvy, it might give you the confidence that they are correct. So then we looked at 1 over x, and that gives us log x plus c, which is one that you need to know, and it's one of the specific types of integration that you may think, well, that's just an answer I need to remember, but it's part of a rule that we're going to see in a minute. Talking of which, we looked at the big 6. So would you be able to name what they were? So the 3 ways of differentiating and the 3 ways of integrating. So that's another chance for you to pause the video. So the 3 differentiation techniques will be, in fact, let's do it the other way. Differentiation technique number 1 is the chain rule, differentiation by substitution. So we're going to, what kind of functions do we differentiate with those? Pause. I'm sure you remember that that's going to be composite functions, or a function of a function, but we call them composite. And we substitute, we put u equals the function of a function, one, this the latter one, differentiate that, differentiate the function with the substitute in it, and then multiply them together. So that's a chain, it's known as the chain rule. Or we can think of it as differentiation by substitution. So that leads us on to the reverse of it, which is integration by substitution. So it's integration of functions that are composite. And we do the same thing, we're going to put u in, but this time we need to eliminate dx, because if we have u equals something and the thing's in terms of u, we can't integrate with respect to x now. Why is that? Can you remember? Have a think about that for Monday. Tell me. So we'll change everything. So all the x functions become u, dx needs to become du, and then we just integrate as normal. The second differentiation technique is the product rule. So that's when we're differentiating a product of 2 functions, which are usually different, and multiplying them together is not able to simplify them. So we can't just differentiate them one by one and it gives the right answer. We have to use the product rule. If you recall, that came from multiplying out the binomial expansion of u plus du, v plus dv, so it was a binomial square. Once we look at the change part of it is just a v du plus u dv. Remember to put the v first, because that will you'll never make a mistake when it comes to this technique. The reverse of that is integration by parts. I'm not really sure why it's called that. It's probably because the integration is split into 2 parts. But I just think of it, where it comes from is that it's derived from the product rule backwards. So that's what I've got next for you, which is what I've started to write here. So the product rule is the du times v dx, so it's the derivative of uv, is v du plus u dv. If I integrate the left hand side, that's going to cancel out the derivative, because it's the opposite, and integrate the right hand side, because I've integrated the left hand, I'm going to end up with that. A bit of rearrangement, and I've got the integral of u dv is equal to uv minus the integral of v du, that should be. And that's it. So we kind of split up the integration into 2 parts, and that's why we do it. It's just a trick, really, to make it. The idea behind it is to try and develop an easy integral here, And if this is easy, then it makes it, obviously it makes the question a lot easier, doesn't it? If we can't integrate something and we just turn it into an easy integral, that's obviously a lot better. The third differentiation technique is the quotient rule. We talked about that, where you have to differentiate, where you are differentiating a division. So it's very similar to the product rule, VDU, except because it's a division, it's going to have a subtraction in it, so it's minus UDV. And because of the derivation of it, which I think I will show you one day, there's a v squared in there as well. And the reason for that is it also comes from a binomial expansion, but you have to use a more advanced one to do it for a division. And do you remember what you will have done it? You know the binomial expansion where it's 1 plus n plus n minus 1 x squared and so on. Well, it comes from that. 1 plus nx, sorry, 1 plus nx plus n bracket n minus 1 x squared over 2 factorial and so on. It comes from that. If you know that, we can have a look at it in the future. So the reverse situation for the integration is when we're going to integrate a division. Now, as I mentioned on Monday, we don't really do very many, we only do really 1.5 types at A level. And that one is the one I mentioned earlier, the log of x, the integral of 1 of x, sorry, gives log of x. And the reason for that is because 1 is the derivative of x. Whenever we have the derivative and the top of the division, or the numerator, the integral of it will just be the log of what's in the denominator, plus c. And we looked at a few examples of that, e to the x over e to the x, sin x, cos x over sin x, and so on. And we found that everything just became log of a thing. And that's something that's used in A level a lot, in what used to be C4. And you don't really do any other division types of integration. That's as far as it goes for A level, because division is a bit of a pain, and there's even more of a pain when you do integration. And mathematicians don't do it, they just look it up in the book. Next up I have limits. That's just the two types of integration. So what we've been talking about entirely so far is indefinite integrals. So when you integrate, say, 2, you get 2x plus c. Even though I'm saying it's giving me an area, it's not actually giving me a value. It's okay, the area of that rectangle is 2x, but I need to put a value of x in to figure out what it would be for a certain place. So if x was 5, that would give me the area of that rectangle is 10, which makes sense because it's 5 long and 2 long, 2 high. What's clever about integration is that I can do it for any strip. So if I wanted to find the area between here and here, and that was 1, I can put 5 in, I can put 1 in, take 1 away from the other, and that will tell me the area of the shaded bit there. Same for curvy stuff. We just find the kind of strips of area from beginning at the origin to moving to the right. If we want to find those strips, then we need to just take away the part we don't want, and that's why you do a subtraction and integration. And we had a look at a couple of those. Then I combined all of that by switching over to trigonometry. We did radians, where they come from, and why we use them. It should be a y in there. So what's a radian? Can you remember the definition? So pause the video. So radian is an angle, or a measurement of an angle, which is superior to degrees. So we don't use degrees in maths because it doesn't fit. It's like a square peg in that round hole. So it just happened to be what someone chose once, and Todd's law, it's not the right one. Radians is actually what the universe works to. Radians is short for radius angle, and there are 2 pi of them because there are 2 pi radii in a circle. There are 2 pi radians in a circle. And we said that 1 radian is 57.3 degrees, to give you a sense of the size of it. So there's 6.28 radians in a circle, or 6.28 in 360. Then I got you to integrate cos x, and we use radians in the integral as for limits. If we put degrees in there, you might think, well, it just work the same, but it doesn't really work that well. It just doesn't fit well. So that's one of the many reasons we use radians. We integrated cos x from 0 to pi by 2, and we found the area of that shape, which I always find weird. was 1, which still amazes me that a curvy shape like that has got the area of a square. But there you go. Hopefully you found that useful and interesting, and if you've got any questions, get back to me. The questions I sent you, if you have any problems with them, please, if you got stuck on one, let me know before Monday. I might not have time to reply, but at least I'll have time to prepare something, an answer for you. It's probably better than me sort of looking at it on the fly. So if you've got stuck on, say, Friday, just email me and say I'm stuck. And if I don't get the chance to respond, I will have looked at it anyway. I'll look at it straight away. I'll be happy to do that. Anything else you want to know or ask me, please email me, text, whatever. Okay, speak soon.